All right, we're back. We're on page 80 of math analysis, and we're solving trig equations. And there's something you may or may not have noticed about pretty much all of the equation that we solved so far, except for literally the first one in this set of notes. All of them have just been of x, secant of x, cotan of x, sine of x, cosine of x. And then, well, this one was not of. I guess the first page was not. But when we were dealing without the graph and without like things to fall back on, everything was just of x. That's obviously not always going to be the case, right? So, and we've already seen it on the first page. So what I want to do is I want to give you a way that you can deal with these where you don't necessarily need to graph. And also sometimes it'll be one of the famous ratios, but not a quadrantal, right? It won't be a maximum, minimum, or intercept. It'll be like a pi over 3 type situation. You'll get radical 3 over 2, or you'll get 1/2, right? And to solve those with a graph is way dicier. So let's take a look at this. Solve each of the following for x by first solving a simpler equation. So the simpler equation is you look for patterns. So here I see x minus 3, I see x minus 3. What if I just replaced x minus 3 and solved a simpler equation? What if I said, let u equal x minus 3? So if u equals x minus 3, then this becomes u squared minus 5u plus 6 equals 0. And then I can solve that by factoring, I think. Minus 3 u minus 2, which means u equals 3 or u equals 2. But because we know that u is equal to, that's not even, trying to use my highlighter, it's not a highlighter. U is equal to x minus 3. So really what we're saying is that x minus 3 equals 3, or x equals 6, or x minus 3 equals 2, or x equals 5. Then if you go back and check, you get plug in 5 gives me 2 squared is 4, 2, so 4 plus 6 is 10, minus 10 is 0. Plug in, plug in 6, you get 3 squared is 9, plus 6 is 15, and then this is 3 times 5, so minus 15. So it worked. So this is a technique that you will find yourself, as algebraic things get a little more complicated, you will find yourself using this more and more often. So here, I'm going to let u equal x minus 5 over x plus 3. And then the problem becomes u squared plus 6u plus 5 equals 0, which is like super close to the last one. U plus 5, u plus 1. It's one of those weird factoring deals. So either u equals negative 5 or u equals negative 1. And then it's still like not super great because u is equal to x minus 5 over x plus 3. So x minus 5 over x plus 3 is equal to 5, which means that x minus 5 equals 5x plus 15. 4x equals negative 20, so x equals negative 5. That's from one of the substitutions. The other one, x minus 5 over x plus 3 equals negative 1. X minus 5 equals negative x minus 3. 2x equals add 5, 2, so we get x equals 1. Wow. So if we plug in and check, you know, I'm just like pretty sure they're right. I don't really want to check. We could check it on the calculator. Let's do that. That's when laziness overtakes you, you know, when you're recording like your 3rd page of notes for the day, something like that. Let the calculator do the work. So I'm just going to have the calculator solve x minus 3 squared minus 5 quantity x minus 3 plus 6 equals 0 for x. I mean, we checked that one, but you know, it was a good idea. So you can actually, maybe you can do this. I'm going to try this. U squared plus 6u plus 5 equals 0, comma x, such that u equals, I don't know what's going to happen here. This might work, it might not. I'm trying to like save myself from having to, negative 5/3. Where are we getting that? 5x, x minus the, interesting. I got one of those answers. I did not get the other one. Oh, let me Let me solve this for u. -5, -1. Oh, I had a copy error. Those are the worst. So a copy error is when you like did the work right, and then for some reason in one step, you just copy the wrong thing. And so that's what I did. So here we go. Let's see if we can find that. It's not hard to find. U equals -5. Look at me using u equals 5. So this is negative minus, disaster strikes. So this will become -6. Jeez. And this will become 20 over 6, which is still not 10. What was I supposed to get? 5/3? That's still wrong. Why is that? Oh, because now this isn't right. Jeez. All right, this is going to be 10 because I'm adding 15 to both sides. Now I'm going to get -5/3. There you go. Good thing I checked that one. So this is the process of u-substitution. We can use this to solve all kinds of trig equations. So what I'm going to do is I'm going to try it on one of these, and then I will come back probably in the next video and finish the next problem and go from there. So here's what I'm going to do. This looks sort of familiar. If this was just u, I'd be solving sine of u equals radical 3 over 2. I can solve that just by thinking. It's going to be pi over 3 and 2 pi over 3. So I'm going to basically do that. I'm going to say, let u equal 3x minus pi over 6. So then my equation is actually the sine of u equals radical 3 over 2. And then you can go through your process, or you can just know it. Sine is positive here and here. I know that the reference angle, do I really need to do this? The reference angle is pi over 3. So I know that u is equal to pi over 3. This is the first quadrant. But I can add 2 pi n to that. Anytime I'm coterminal, it's going to work. Sometimes you skip the n as an element of the integers until like the very end. That's totally fine. Or u is equal to 2 pi over 3 plus 2 pi n, where again, n is an element of the integers. Okay, but we weren't asked to solve for u. We were asked to solve for x. So we're going to make this substitution for every u that we see. So I'm going to take this down here and say 3x minus pi over 6, yikes, equals, so we need a common denominator to like efficiently do the math. So I'm going to change this from pi over 3 to 2 pi over 6 plus 2 pi n. I'm gonna save the n as an element of the integers for a second here. So 3x equals, if I add this, I get 3 pi over 6, which is pi over 2, plus 2 pi n. So x is, divide everything by 3, pi over 6 plus 2 pi over 3 times n, which is why it's so important to generalize as soon as you can. Because if you're going to multiply or divide by anything, you got to multiply and divide everything by that. So make sure you generalize as soon as possible. So we get this, where n is an element of the integers. And then also, we got to do the other one. So we go down here, and we say, maybe I should do this. Let me undo that. And then, you know what I'm going to do? I'm going to do a little rearranging here. So that's not how that works. Here we go, rearranging. So I'm going to move, this is going to look a little weird. I'm moving this over here where I like lost part of my arrow. I'm moving that over there. I'm going to move this over here. Then I'm going to move this up. I'm going to just fix my arrow in a second. And then I'm going to delete the arrow. Okay, I think that's good. I don't know. I'm going to do the same thing here. So u becomes 3x minus pi over 6, which equals, I'm going to make this 4 pi over 6 plus 2 pi n. And then that means, so I'm adding, so I get 3x equals 5 pi over 6 plus 2 pi n. Then divide, I get x equals 5 pi over 18 plus 2 pi over 3 times n, where n is an element of the integers. So we could have, if you look, so common denominators are like a big deal when you're doing this because getting common denominators like feels right. So here we ended up over 18. If you go back to this work, if I had left this as 2 pi over 6, and then it would have been 3 pi over 6, and then it would be 3 pi over 18, we'd have 3 pi over 18, 5 pi over 18, it would feel better. So I'm going to be back in the next video. I'm going to start off by checking these, and I'm going to try to do B, and then I guess that's it. And then, you know, get the calculator to just do all the problems. But I'll be back in the next video, and I hope to see you there.